I'm just going to talk today about one of the research topics that we're studying in the crac lab, okay, and it's related to air quality, it's related to particulate pollution in Ireland, and really from solid fuel burning, as we see, which is a major problem, okay. I want to talk a bit about the history, which goes back to the Dublin Smog of the 1980s and the introduction of the coal ban, and how we've moved from black smoke as a simple measurement of pollution to what we call particulate matter, and then identifying sources of particulate matter, and our latest research project called SAPPHIRE, which is looking at quantifying sources of particles in the atmosphere and really focusing on the solid fuel burning problem that affects especially small towns. Okay, and then I'll kind of wrap up and I'll try and keep it to about 20 or 25 minutes or so. So let's go back to the Dublin Smogs of the 1980s. I don't know if many of you know about them, but they were certainly a big issue at the time. Coal burning was the major source of home heating in the 1980s in Ireland, and Dublin, being a large city, had quite serious air pollution problems with that. Okay, not too different from the London smog problems of the 1950s, in fact. And in 1984, this paper was published, and it really focused on probably the first study of linking air pollution and its impact on health in Ireland. Okay, and so what we did here, we have one particular smog event in January 1982, where we have black smoke measurements here, going very high, up to 800 micrograms per meters cubed. Okay, so that's the concentration term for black smoke. And here we have the number of deaths recorded in only one hospital, just in one hospital in Dublin. Okay, and you can see that as we have a spike in black smoke through air pollution, we then have a corresponding rise in number of deaths. And that rise in deaths is actually maintained even for a few days afterwards. So this is exactly the sort of thing that was seen in the London smogs of the 1950s. And exactly as in the London smogs of the 1950s, it really was due to solid fuel burning in winter months when we had cold weather, temperature inversion, which is like a lid on the lower part of the atmosphere, which prevents dispersion, along with low wind speeds, which further prevent dispersion, and we have correspondingly very high levels of black smoke and also sulfur dioxide, sulfur compounds being an important component of coal. Okay, so you can see that the number of deaths per day here basically doubled during the smog event and remained high for a few days afterwards. So that was published in the 1980s. As we know, Ireland in the 1980s was quite different from what it is now, and in fact nothing much was done about it. There were lots of complaints about air quality, but there wasn't even an EPA in Ireland in the 1980s. And it wasn't until 1990, and this was really due to large political pressure, with the introduction and establishment of the EPA, that was also something eventually came in. I mean, in 1988 to 1989, it was a very severe smog event. These are pictures from Dublin in 88, 89. This is 1989, this isn't that long ago. And people just, I think this guy is probably even going out to buy more coal. You know, it's crazy stuff altogether, right? And so this was stuff that should have been got rid of decades ago. In the end, there's a ban on smoky coal in Dublin, and this was brought in 1990, along with the establishment of the EPA. Okay, and we can see it had an immediate effect. All right, here is a plot which shows you the black smoke concentration measured as a seasonal average, the black dots being winter, and you can see peaking in winter months every year. Okay, coal ban introduced, woof, that's a massive drop. Okay, we also see a corresponding drop in sulfur dioxide too. So the effect was immediate in terms of air quality, and in fact, a period later, when the same guys that did the original study looked at all hospital admissions data, they looked at the impact of this, and what they found is that in addition to there being obviously reduction in black smoke and sulfur dioxide, there were actually a lot less deaths due to exposure to air pollution. That's 116 fewer respiratory deaths and 243 fewer cardiovascular deaths. So by implementing the ban on smoky coal, there was over 350 lives saved each year in Dublin. So that impact is huge. Okay. Obviously other places around the country said, it's good for Dublin, that's good for us. Okay, and in 1995, Cork City, the ban was implemented and extended to other towns around the country in the late 90s. And here we got a plot which summarises the changes in black smoke. Dublin is in blue, and we can see that here the concentrations for black smoke in Dublin are really quite high. 1990 they drop, and they get lower and lower as time goes on. From 1990, Cork takes over as being the most polluted city. Okay, Cork shown is in yellow here. Concentrations as high as 200 micrograms per meter cubed. By 1995, a ban in coal, smoky coal in Cork City, and Limerick takes over. Okay, and you can see the effect there. Maybe the effect in Limerick isn't so pronounced. Okay, but you can certainly see that there are significant benefits of a ban on smoky coal. And this was extended throughout the country to smaller towns, and basically towns with a larger population were those that were first brought into legislation. Okay, and it's growing through time. Even as recently as 2013, these sorts of towns were included in the ban on smoky coal. During this time period, what has happened is that our understanding of particles in the atmosphere has changed. It turns out that black smoke is not very well defined, and we've now been able to more accurately define different types of particles, which we call particulate matter, and these were brought in 2005. The black smoke standards are gone, and in the European Air Quality Directive now, so this is actually embedded in legislation, we have definitions of particulate matter. And two that are very relevant is PM10, which is particulate matter with diameter less than 10 microns, and PM2.5, which is particulate matter with diameter less than 2.5 microns. What do these look like? Well, you can't see them, okay, because here's the width of a human hair, okay, so it's of the order of about 70 microns. So a PM10 particle is one of these blue dots on here, okay, so they're invisible to the eye. You can see them under microscopes, of course, and PM2.5, obviously there's 4 of those to the diameter of a PM10 particle. So these are tiny, you can't see them, okay. But that doesn't mean to say they don't have an impact, because they do. And this is really the reason why PM10 and PM2.5 are defined, is because PM10 is the size which can start to enter the respiratory system. Okay? Particles bigger than about 10 microns are actually filtered out by nasal hair. Even the back of our throats can cough up large particles. If you get dust and stuff, you start to cough, and that's a mechanism to get rid of large particles. And the smaller particles can get down into the lungs, and anything smaller than about 2.5 microns gets into the lungs. And so they have a more dangerous effect, and that's why the PM2.5 classification exists. And even smaller particles, less than a micron, can penetrate alveoli and cause some real serious damage to cells. Okay? So PM2.5 and PM10 are the ones that are really focused on in terms of air quality legislation. And the health effects of exposure to particulate matter are really well documented now. There's been lots of research over the last 10 or 15 years. The effects of short-term exposure to air pollution include respiratory and cardiovascular problems, like aggravation of asthma, okay? Long-term exposure includes things like generation of respiratory diseases and even lung cancer. Okay, and PM10 and PM2.5, because of that, they're classified as air pollutants, and limits on their concentration are part of the EU legislation on air quality. So, as a result, people are interested in monitoring them. We have to obey this legislation. Okay, we have to make sure that levels are within the limits. Okay, and the EPA and local authorities around the country have various monitoring sites. Okay, this is from the EPA Air Quality Report 2013. So we monitor PM at many locations around the country, 2 places in Cork City as it happens. Okay, and what these do is they obtain daily average values for concentration in terms of microgram per meter cube. So this is just one number a day. Okay, and I'll show you where there's limits on that later on. When we look at the air quality of Ireland, how polluted is Ireland? Well, what we see is that, in fact, compared to the limit values for PM2.5, which is shown up here, the limit value is 25 microgram per meter cubed. Well, we're actually way off that. Okay, so you might think that the air quality is good. And then you start to look a bit closer at some of the different monitoring sites here. Okay, and what you can see is that actually here is Coleraine Street, Dublin, Rathmines, Dublin, okay, Marino is Dublin, Old Station Road, Cork, and what we see is that actually the cities have air pollution that isn't so bad. But the small towns, look here, for example, in blue is Ennis. Okay, so in 2010, Ennis, you could say, was the most polluted place in Ireland. Why Ennis? It's not as if it has loads of people living there or lots of pollution from traffic you might expect, but of course it's solid fuel burning, as I'll go on to in a bit more detail. The World Health Organization take an annual assessment of all the research on the health effects of PM, and they put forward an air quality guideline limit value of 10. And we can see if we look at that metric, then air quality in Ireland is actually above that. Okay, so it's not as good as that. Okay, so that is what the EPA is striving for, is to improve air quality so that we meet the World Health Organization clean air quality guidelines. Why? Well, because exposure to PM 2.5 reduces the life expectancy of a person in Europe on average by 9 months. So that's every single person in this room. Your life expectancy is reduced by 9 months by exposure to air pollution. That's on average. Okay. What is also really been established is that there is no real safe level of exposure to particulate matter. Okay. So even if you say the limit's 10, even if the limit is 2, you could still be exposed to particulate matter that could damage your health. Okay. So we should continually strive to get lower and lower levels of pollution. And there is already from the USA clear evidence that health benefits can arise if PM levels are reduced. Less hospital admissions, and this also affects the economy, less impact on the health service providers, etc. So we're interested in reducing particulate levels in the atmosphere. How can we do that? Well, we need to know and to quantify the sources. We need to know how much is produced from traffic, how much is produced from solid fuel burning, how much is from natural sources even, how much is from industry. Okay, how do these emissions vary during the day and by season? Okay, so we need to find out a lot of detailed information. And the best way to do that is not to measure at one site to give one number a day, it's to do highly detailed, high time resolution measurements, not just looking at the particles or their mass, but what they're made of. Because it turns out what they're made of is a good indicator of where they come from. And that's what we're going to look at. And once you get loads of data, you can actually model the different sources and try to quantify their contribution to the overall levels that we observe. So this brings me on to our current project, which has been in place for about a year now. It's called SAPPHIRE, and we're looking at the sources of particles mainly in residential areas of Ireland. Okay, so we're halfway through that. It's an EPA-funded project, and we're looking to quantify the major sources of PM 2.5, and we're looking at small towns because we know that they have air quality problems due to solid fuel burning, especially in winter months. And the idea is that this should feed into policy that the Department of the Environment might make on changes to reduce particulate pollution. So we need to go outside. We've got to get out of the lab. We've got to take some equipment outside and measure what's going on. And we need to choose sites that are representative of small towns where they might have winter air pollution problems. And the first location was Killarney. Okay, it's a good candidate because it's a small town. It's not under Smoky coal ban. It's off the natural gas. Okay, so there's no natural gas, so there's going to be a high level of solid fuel burning. Okay, and we managed to get a location in a place called the Community Hospital, which is on the western part of the town here. Okay, it's kind of linked nearby a residential area. All right, and you know Killarney is not very highly densely populated or anything, and in fact you can see here's the national park, it's just behind here. Okay, so it's quite a clean site in reality. Okay, but there is still residential activity all around. So what we do is we go to we chose this site and we take all our equipment, which includes an aerosol mass spectrometer, particle sizes, devices for collecting samples, and we take our van and we've got a container here. We have lots of sample inlets on the roof, and we set up and park there for about a month or two and see what we get. Here's the range of instruments that we deployed at this location. All right, so we have an aerosol mass spectrometer, more about that in a minute, but that gives us the chemical composition of particles. We can measure the size of the particles. For from about 10 nanometers up to 10 microns. So it covers the whole range up to PM10. We can measure the mass concentration. We can look at carbonaceous aerosols. We look at the elemental and organic carbon. All right. This is another device for looking at elemental carbon. It's called an ethylometer. We can also collect samples for analysis later on in the lab. We've got some gas phase analysis, and we've also got weather information as well. Okay. So there's a whole lot of equipment that is deployed that runs at high time resolution. That's the key. Okay. So let's look at some preliminary analysis. This was done in November and December. Okay. And we can see here this is going through from about the 12th of November through to the 20th of December, and this is the trace of PM2.5 mass concentration. Okay, and what we see is we have a general bobbing along baseline with regular spikes, and of course those regular spikes occur during the evening times, and we can even see here that those regular spikes go up to about 120, 140. Whereas the background level is about 10. So we're getting levels at night time which are of the order about 10 times higher than they are during the day. So we're getting really high values at night, and they can persist for quite a long period of time. The red, okay, squares indicate the daily average. So if you're there as the EPA are, just looking at daily average, you might see, oh, we only got 18 today, or we got 12 today, or we got 20 today, or we got maybe 50 here today. That's a polluted day. Okay, but we know when that pollution occurs, and only occurs for a short period, and it's a very intense burst of pollution. Okay, as you can see on the next slide, because here is now a 24-hour cycle of mass concentration, and we can see the levels are really quite low. There's a little bump in the morning. This is due to traffic, we expect. Okay. And as we go through the early evening now, we start to see increases, huge increases, okay? And this is through the whole period. So this is a 24-hour cycle, average across the whole period, and we can see that peaking at 7, 8 o'clock at night when people are obviously setting down fires for their home heating. So we have overall about 6 or 8 hours of elevated PM2.5 levels. They're so high, but the other parts are so low, okay? Why this is important is because if you are asthmatic and want to go for a walk, you wouldn't want to pick that time, because this could aggravate your asthma. Okay? If you're asthmatic and want to take a dog for a walk, let's go out at 2 o'clock in the afternoon. 2 o'clock in the morning might be even better. Okay? So that sort of information is very important in terms of protecting health. Okay? Now, you're kind of implying that peaks of PM during the evening are due to solid fuel burning, but can you prove it? Yes, we can, and we can prove it by looking at the chemical composition, and this is the chemistry bit. All right, we use an aerosol time of flight mass spectrometer, so it looks at the aerosols, and it uses mass spectrometry with a time of flight detector. Okay, so you've covered that in some of your lectures. What happens is that the particles come in, okay, in the top here is a sample area, and they go down into an area here where they're sized, they're hit by lasers, and this gives their size. Okay. This then goes down to a high vacuum, so we only get a single particles, a beam of single particles going down, and these lasers serve as triggers for another laser down here, which actually starts to hit the particles and break them up and ionize them into gas phase ions. Okay, and so we have a positive and a negative mode mass spectrometer in the time of flight. All right. The result is that for every single particle that we hit, we get a mass spectrum of the positive and the negative mode. So this is an example for sea salt particles that you might get. Obviously we see sodium in the positive, very strong, and we see chloride in the negative. But we also get some extra information. You'll see some nitrate and sulfate, which shows us that this sea salt particle is a little bit processed. It's picked up nitrate and sulfate from atmospheric processing. So you get an idea of the source of the particle based upon its composition, and also any chemical processing that has happened to it during its transport in the atmosphere. Here's another example. Biomass burning. This is wood burning, okay? A very strong potassium signal. All living stuff has potassium in it, right? And you get that dominant peak in the positive mode. In the negative mode, you get a whole range of stuff, including nitrate and sulfate, but lots of carbon and some organic carbon fragments too. Okay. So when we operate our aerosol time of flight mass spectrometer, we get lots of data. It's scanning, collecting information all the time. So over a 5 or 6 week period, we'll get 500,000 mass spectra. What you do with that, well, you don't sit down and sort them out one by one. You have these algorithms which you use to sort the data, okay? And so we use a K-means algorithm. This is a freeware that's available, okay? And what it does, it sorts out the particles based upon their mass spectra into different types. So we might get, say, 50 types of particles, okay? Each with different numbers, okay? And then at some point, the user comes in and starts to combine them to really simplify that, because 50 is too much. We're looking at about 10 or 20 different types of particles. Okay. What we then do is we have each particle type as a mass spectrum, and based on that mass spectrum, we can assign it to a source, or we can assign it to some stuff like elemental carbon or sodium chloride or whatever. So we typically name them after their chemical composition or their likely source. And for solid fuel burning, we've done some experiments where we've got unique signatures for coal, for peat, and for wood. So we use these to identify coal, wood, and peat burning particles in the ambient data set that we collect. So on to the results. So this is the measurements from Killarney, okay? So this is from just over 3 weeks running, okay? We have about 500,000 mass spectra, and what we're able to do is we're able to assign all the particles that we detect to different particle classes. And we can see that we have wood and peat being very dominant, okay, in terms of the numbers of particles that we observe, okay. Coal only makes a very small contribution. We have some other types of particles, ECOC, which I'll show you in a minute, just carbonaceous. They're hard to pick out exactly. They don't necessarily have such unique markers, but their timing is exactly the same as that of coal and peat. So we think they're likely associated with coal and peat. So all of these are due to domestic solid fuel burning, and that's 78% of the particles. So that's a huge contribution. We also see some sea salt, which is natural, kind of not too far from the sea. So this is really carried in from the ocean, especially on windy days. And we see some other small types of particles, including traffic, okay, which has a unique marker as well. But it's only very small. How about the time, the temporal profile? Okay, well, it's quite complicated, but we have fuel combustion particles. So all of these, apart from one, are fuel combustion particles. And in fact, their features follow exactly the PM mass that we showed earlier on. You've got coal, peat and wood, and this ECOC, elemental carbon, organic carbon class, follows that exactly as well. Okay, so they all follow the same pattern of solid fuel burning. Apart from this sea salt one here, which you can see here, this is a very windy period, and you can see that we have high amounts of sea salt being blown in from the ocean, and this has meant that even though there's probably solid fuel burning still going on, we get much more dispersion. Okay, so we can't take our eyes off the weather. We've got to factor that into our analysis as well. All right? Here is the 24-hour cycle of counts, which peaks in the evening, just like our PM mass concentration as well. This is all the particle types now. And when we separate that into the different components, here are all these solid fuel combustion ones, okay, again peaking in the evening hours. Here is traffic, as you might expect, a peak in the morning, between about 9 and 11 o'clock. Here is sea salt, okay, going on a 24-hour cycle, no real pattern, as it just depends upon the wind. So that all makes sense to us. Okay. So it turns out that just as in the Dublin of the 1980s, smoky coal, or a restriction on solid fuel burning, is actually a hot topic. The ex-Department of the Environment Minister, which is Phil Hogan, was trying to make a move on a nationwide ban for smoky coal. Okay, and there are advocates for that as well, including the Asthma Society for one. Let's have a ban on smoky coal. Hill and Scothie is interesting because it's also a small town, no smoky coal ban, no natural gas, but it's in a valley, and there's real air quality problems associated with that, less dispersion. And we set up there with the same setup, and preliminary analysis shows quite a different picture actually. Coal is the real dominant feature here, but also with peat burning, very small wood. So we're switching peat for wood here now. Peat in Killarney, coal in Scothie. And maybe if you look at the sales of solid fuel, you might see that's actually reflected in that as well. Okay. Interestingly, we got some polycyclic aromatic hydrocarbons, a large amount of these particles. This is only preliminary analysis, but this is quite concerning because pHs are toxic, right? And if we really get lots of pHs, then we really need to look closely at this and see if we can confirm this preliminary research, these preliminary results. We get the same time series, it's amazingly regular, of the solid fuel burning. So we have coal and wood here, and peat, coal and wood, peat, coal and wood, peat, coal and wood, peat, coal and wood, peat, and so on. It's amazingly regular, so obviously solid fuel burning. Okay, the pHs, ECOC, coincide with that very much. Okay, so in fact about 80% of the particles from Enniscorthy are also due to solid fuel burning. So just to wrap up, okay, I'm not going to say that we live in a very polluted country, because we don't. Air quality in Ireland actually is generally good. We don't have the problems that Paris or London has. Okay, but we do have a different type of problem, which is that particulate pollution is a problem in small towns during winter months, especially where there is a no smoky coal ban in place. Okay, previous work from Cork, actually, even where there is a smoky coal ban in place, showed that 50% of the air pollution of the PM2.5 is actually from solid fuel burning. And preliminary results from this research that we're currently performing indicates this could be as high as 75% in Enniscorthy and Killarney. Okay. Small towns should have clean air, but they don't. So, just to summarise, from a health and environmental perspective, it makes sense to support a nationwide ban of smoky coal. You will get improvements in air quality. How well will it work? Can it be policed? Can it be looked after? Well, yeah, it could be, but will people just burn more peat and wood? And in fact, we see peat and wood particles everywhere as well. So they also produce particulate pollution. So in the longer term, a smoky coal ban may not be sufficient, and we will have to look at stuff like renewables, cleaner fuels, and more efficient burning technologies like stoves and so on. Okay. So that's just a wrap up. The people who've done the work really are Ian, Owen and Giovanna, especially on this project. Paul Buckley helped out a lot with Killarney, and Stig is stepping in now to do some source apportionment, and John Sodder has gotten us some nice publicity down the line as well. So thank you very much.